Good morning. So I just want to start with kind of like an overview of what we have done in the last two lectures. We looked at graphical method and bisection method. And if you think about those methods, bisection method is what is called as a bracketing method, meaning you need to specify a range in which you are likely to find your root. False position method is a similar variant of that idea. So I'm for the moment skipping false position method. I'll cover that on Thursday. And then we go on to the next type of methods, which are called open methods, where you need to guess only one value. That is, you need to guess a potential root. And from that, you iterate and zero down on what is the exact value. Okay, those are called open methods. Bracketing means you need to find a range. Open means you need to guess one value and then work on from there. So within that, we are going to see what are called Newton-Raphson and secant methods today. For the quiz on Thursday, graphical method, bisection method, Newton-Raphson, and secant. Those are the four topics I'll be testing you on. Okay, 1, 2, 5, and 6. Okay. On Thursday, I'll be covering 3 and 4 after the quiz, like after the first 40 minutes. So for the exam, all 6 are fair game. But for Thursday, 1, 2, 5, and 6. Is that clear? Okay. And I also wanted to tell you about, so if you see here, I have a quiz. This is the quiz I'll open on Thursday, print copies and bring here. I won't open it now, but I also prepared a mock quiz, which you can see here. So here is the exact format in which you can expect your Thursday quiz to be. 2 problems, an equation, a function is given to you. Problem 1 is solve that function, say using Newton-Raphson method, and I'll give you some potential guesses, and then you'll have to iterate and fill up this table. Okay, we'll see Newton-Raphson today. And problem 2 is solve the same equation using bisection method with initial guesses, so on and so forth, and fill out this table. So it's 2 problems, 40 minutes. You can bring 1 sheet of notes. No textbook, only 1 sheet of notes. Okay. And in this mock exam, I put bisection method and Newton-Raphson method, but it could be bisection, Newton-Raphson, or secant method. Graphical method is not a real method in my book, in the sense that it's not something with which you can get a final answer. So you are welcome to use it as you see fit. Okay. 2, 3 methods: bisection, Newton-Raphson, secant, 2 problems. Okay. And here's the format. The same equation solved using 2 methods, so you'll have something to compare against. So if you get one completely wacko answer with one method, you know something is amiss. Okay. All right. And I also posted the solutions to these 2 problems, which you can look at and compare your work. So if you look at this problem here, say, oh, that's the solution to the actual quiz. Okay. No, not again. Quiz 1 mock. Yeah. I should keep a separate folder. Okay. Playing on the edge here. All right. So this is the function. If I graph it, if I look at it, there are 2 roots. I use the graphical method to identify the range or an initial guess, and then I present to you the solution using bisection method and then Newton-Raphson method. So this is for you to practice and check against. Okay. So no complaints that I didn't tell you what's coming. Nobody can be more precise than this. Okay. All right. If you just a reminder, if you go to the syllabus, I keep updating the YouTube link for each lecture so that you know what exactly was covered on each day. And I strongly urge you to go home, if necessary, watch the lecture again to see what you missed, if necessary. Okay. All right. Any questions? Yes. Sure. Yeah. Sure. Maybe. Don't bring an iPad, but graphing calculator is okay. So each time you ask me, can I use this technology or that technology, you're just forcing me to think more, which is okay. All right. So we talked about bisection method. So if you have a function that is crossing zero at some point, so this is what f of x, this is x. So if it crosses f of x naught is zero, you are trying to determine what is x naught. That is the whole process of finding the root, right? So you identify a range, and within that range, you try to zero down on what is x naught by iterating with a plus b equal to 2. This is the essence of bisection method. This is the essence of bisection method. Okay. When we go on to other methods which are called open methods, we don't want to be guessing two values. Why? Because guessing two values requires knowledge of approximately where the curve intersects with the x-axis, which means you need to do graphical method, which is more work. If you want to do less work, what you want is a method that works with only one guess, okay, which is what we call open method, okay. So if you consider this curve here, okay, we'll draw it separately. Suppose you consider any point x. What is the value of the function at that point? That's easy, f of x. Because your goal is to solve for f of x equal to 0. That is your goal. If this function is given to you, like in the exam, I'm telling you f of x is, in your mock exam, the f of x value I've given is something like, should be careful to open the correct quiz, not the real quiz. I have e power minus 0.1x minus sine 2x plus cos 4x. That's the function I've given you. Okay, if you know the function, if f of x is known and differentiable, that is, its slope is well defined at that point, you can also compute f dash of x at any point. Can be evaluated. Right? Would you agree with me? If the function is known and it's a analytic function, you can get the derivative, can't you? Right? So what is the derivative? F dash of x. And what is the function? F of x. Okay. So if you take a value, if you take f dash of x, okay, and suppose this is like a guess value that you start with, we call it xi, okay, and then the next value we want to get, let's say that's going to be at the root and xi plus 1. If xi plus 1 were to be the root of f of x equal to 0, then obviously f dash of xi plus 1 I'm sorry, f of xi plus 1 equal to 0. Would you agree with me? If the next step is putting your foot on the root, by definition, that should make the function 0. Right? Simple idea, right? This is an initial guess, okay? This is some guess that I came up with. Could be anything. All I'm saying is, using the Newton-Raphson method, if my next iteration is going to yield the root, if that were to happen, then that value should make the function 0. You with me? Good? Good? Okay. So from your good old trigonometry, what is slope? You have a triangle. If this is delta x, this is delta y, what is slope? Y over x, right? Delta y over delta x. This is your trigonometry, high school. And then when you came to college or maybe in your senior year of high school, they said that in the limit that delta x is really small, delta y over delta x becomes what is called as dy over dx, or the derivative of x, or derivative of y with respect to x, right? And if y is what we call f of x, then this is nothing but f dash of x. Good? Are you with me so far? Right? So you can write f dash of x as the change in the function value of the function divided by x itself, or you can approximate. This is nothing but f of xi minus, I'm sorry, this is nothing but f of xi plus 1 minus f of xi divided by xi plus 1 minus xi. That is, I'm drawing my triangle over right here. Except f of xi plus 1 is 0. Why 0? We just made that case. If it's the root, it has to satisfy the function. So if you rearrange this, you're going to get xi plus 1 equal to xi minus f of xi divided by f dash of xi. I hope this is coming on camera.
On the last YouTube video, I couldn't really see the board because it was like,
Screen share?
yeah, it was screen share on, so I couldn't see the board. It was like options.
Oh, okay. I'll be careful. Sorry. Thanks for letting me. Okay. Are we all together until here? How we got this, right? This equation or this scheme of iterating for the root of the equation is called Newton-Raphson. Poor dude, Newton got stuck with, Raphson got stuck with Newton, who is super famous. Yes, too. Maybe, I don't know if Raphson has his name on many things, but I'm sure Newton has. So this is your equation for Newton-Raphson. Okay, the steps to solve that problem or solve problems is guess a value for the root. Can be pretty much any real number. The closer you guess it to the root, you're saving iterations, but it can be pretty much any real number. Guess a value for the root. Use xi plus 1 equal to xi. So this guess value, we can call it iteration 0, I equal to 0. Okay, xi plus 1 equal to xi minus f of x divided by f dash of x. Sorry, f of xi divided by f dash of xi. We'll do an example, but just writing the steps first. 3. Compute the residual defined as xi plus 1 minus xi divided by xi as a percentage. Yeah.
How would you guess the value of the root?
It's pretty much any real number you can think of.
Okay, so you think
You could look at the graph, and we are going to see this through an example. That is, you can look at the graph of the function, And if this a function like this can have multiple roots. If you guess it near a particular root, you will gravitate towards that root. If you make it towards nearer the other root, you will go and find the other root. So as always, graphical method will help you identify a good guess. Okay, we'll do this example. I'll walk you through. So compute the residual and repeat until the residual is less than some chosen tolerance. The chosen tolerance can be like 10 power minus 6 or 10 power minus 3 or whatever. And you have to keep repeating these two steps actually. The guesses, so repeat until residual is greater than some chosen tolerance. The moment it goes below the tolerance, you can stop. So this is your algorithm or pseudocode to implement Newton-Raphson method. I know what you're thinking. I need to wait until class gets over, open MATLAB and program this damn thing, right? That's what you're thinking. Okay, so now let's do this example and we'll try to put everything together. Okay? I'll give you 1 minute to finish right. Okay. All right, so this time I'll be very careful. First, I'll share my screen and I'll open my file. 1 second. So quiz 1 mock solution. Okay, I need you to just drop your pencils and listen for a couple of minutes and then continue. So don't miss this. Take a break. All right. So at the top here, that's our function. Okay, I'm going to use the second spreadsheet here. At the top here, that's our function. F of x, and then I also computed f dash of x. Did I do that right? Yeah, minus 0.1. Yeah, everything looks good. Okay. So idea is if you know f of x and if you know differentiation, you can get f dash of x. Okay. And then before you start, be it the exam or be it the homework, always graph the function. Always graph the function. So I have here. So I chose the interval -1 to I think -1 to 3 or something. Yeah, -1 to 3. I took that interval. I graphed the function in that interval. Why did I take -1 to 3? Because I know this exponent will quickly become 0. It's a decaying exponent. So on the graph here, I identified two roots. One is between 0 to 0.5, and the other is between 1 and 1.5, somewhere. This is basic information you should always do whether I ask for it in the problem or not. Okay. So you have this information. If you select a guess value that is closer to this first root, you are going to end up with this root. If you choose the initial guess that is closer to the second root, you will end up finding that root. It's as simple as that. Okay. So if I go up, to my first guess value is 1. I am guessing 1. Okay. Why? Because I see here on the graph, it's intersecting somewhere between 1 and 1.5. I'll just choose 1 and see what happens. So I can easily write what is f of xi, which is I need to punch in 1 here and compute this. What is f dash of xi? Punch in 1, write it here. And this is the Newton-Raphson formula. Xi minus f of xi divided by f dash of x. Very straightforward. Okay. So once I get that, I continue iterating and I also compute the residue. And in each step, this is really simple if you try it. So let's keep this as a reference. We know what the answers are expected to be. You're going to not use your laptop, but do pencil and paper calculation now. Okay? Because this is what you're exactly going to do on Thursday. 20 minutes roughly for each problem. Okay? So forget this exists, start. Your function is this. I'm going to do it with you. Okay? So here's our function f of x given to us. What is f dash of x? That will be minus 0.1 e power minus 0.1x minus 2 cos 2x minus 4 sine 4x. If you have trouble with doing differentiation and you always make mistakes, you are setting yourself up for a lot of failure in this class. You need to be able to do differentiation and integration correctly, quickly. Okay? Okay, so I'll keep the steps here and I'll erase this. For such iterative techniques, I recommend drawing a table. It keeps things organized for you. Iteration number. We'll call it 0. That is, this is I equal to 0. This is our xi. This is f evaluated at xi. This is f dash evaluated at xi. And then we'll say xi plus 1 equal to xi minus f of xi divided by f dash of xi. And then we'll say residue is absolute value of xi minus xi plus 1 minus xi divided by xi expressed as a percent, or not even as a percent, just as a ratio. Don't be like try to memorize this. This is the new value minus the old value divided by new value. Are we together so far? Nobody's feeling terribly lost? No? Good. I'm sure you have written this down, so I'm going to erase this. Okay. You can either always use graphical method to come up with an initial guess to identify a reasonable initial guess. And in our case, we are going to start with 1. You may start with 1.09 or 0.97, it doesn't matter. What is f of 1? This is where you build speed. You need to do this in real time in the exam, so try. What is f of 1 if this were your f of x? Remember, x is in radians, not degrees. E- As a rule of thumb, I am suggesting to all of you to maintain 4 decimal points in all intermediate calculations. You're right though. You're saying 0.6581, correct? Yeah. So what is f dash of xi? F dash of 1. Yep. 3.7690. Regardless of the number of digits before the decimal point, maintain 4 decimal points in intermediate calculation. So xi plus 1, the next value will be 1 minus 0.6581 divided by 3.7690. That is the calculation you need to punch in. Whose bottle is this? What is this value? 1.1751. On 0.17, I'm getting 1.1746. 46. Okay, small difference. 1.1746. We are all able to get this. What is your name? I forget. Santiago. Getting? Yes. Mary? Yes. Okay. All right. How do you compute residue? Residue is always new divided by old minus 1 absolute value. That would be 1.1746 divided by 1 minus 1 as a percentage, which would be 0.1746 or 17.46%. What does 17.46 mean here? Means you are 17.46% away from the target. You are aiming for the target. Okay? Target being the root. So that is the 0th iteration. Then we'll say I equal to 1. Xi is now this value. 1.1746. Compute f of x, f dash of x, repeat the drill. Okay, what is this? Are you getting these values for the f of x, f dash of x, and then the next value? Yeah. That will be 1.1439. Easy for me to say I have an Excel sheet. Also that I'm not the one taking the test on. Yeah.
The quiz, we're not gonna be allowed to use Excel.
No, on Thursday's quiz, it's only pencil, paper and calculator and one sheet of notes. Sorry? You can still plot the graph, you can hand sketch it, you can do approximately. Nobody's asking the graphical answer to be precise. Or you can bring a graphing calculator. And then what is the residue? Residue is new minus divided by old minus 1 absolute value. How much is this? Zero 0.0261 or 2.61 percentage points. Are you getting it?
2.7. Is the new I 1.17 core series?
Yeah.
One.
This is for the previous iteration. This is for the current one. New minus old divided by old minus 1. Yeah.
And you have XI up there, photon. And one over here.
Yeah, I mean, I just, you can write this as xi plus 1 divided by xi. Xi plus 1 is what I call as the new. Xi is the current or old.
Yeah.
Yeah.
But you subtract it by one,
Yeah,
you subtract it by the XI. Divided by XI.
which is the same as subtracting by 1. Like if I, this
Oh.
is nothing but xi plus 1 divided by xi minus 1, isn't it? Yeah. Just think intuitively. You take this value, divide it by this value, and subtract 1 from it. That's it. Okay, next iteration. Iteration 2. This comes here, 1.1439. Compute the f of x, f dash of x, compute the third value, the new value of x. How much is this? Are we all able to get these values? Yes, no, working through it. Totally no idea. Might as well not be here. The key to doing well in the quiz is speed. Speed and accuracy. You need to practice, need to be able to do this in 20 minutes and be sure you're right. Okay. In the quiz, there are two problems. In the exam, in 60 minutes, we'll pack in 4 problems. That's 15 minutes per problem. Quiz is 20 minutes per problem. So I'm kind of squeezing you further in the exam. So you need to work on your practice. Okay. Yeah.
So to get like X.
F dash, the derivative.
Yeah, so you. That's not on the sheet, you just calculate it.
It is there. Um,
On mock quiz.
sorry, the mock quiz solutions. Yeah. One second. So anyway, I wanted to show some things on the Excel sheet. So now take a pause. Let's look at this so that we can wrap up this discussion. So here's the problem statement. It says this is the function. Solve for f of x equal to 0 using Newton-Raphson method with an initial guess of 0.5 or 1. Each guess will lead you to a different route for this function. Perform iterations until the relative error falls below 10 power minus 6 or 5 iterations, whichever is earlier. So I've even given you the table. All you need to do is fill in the blanks. The initial guess, the function, the derivative, the next value, the residue. Do this step by step, fill up the table, and you are, by the end of 5 iterations or even sooner, you are done. Is that what you were referring to?
No, I mean, like, I like in the mock quiz.
This is the mock quiz.
No, like in the mock quiz, we got the data X.
This is the mock quiz solution. Okay, let me share my screen. All right, this is the mock quiz solution. I have the function, the x value, function, derivative, and the value of xi plus 1 in the next iteration. And I do this 0, 1, 2, 3, 4, 5. The problem statement said, keep doing this until either this residue falls below 10 power minus 6, which is anything that has one more decimal point is less than 10 power minus 6, or 5 iterations, whichever comes sooner. It just so happened it came by the 4th iteration. So you did everything right. You can look at the residue and think it's already there. I can stop. Yes.
Collisions.
In the
I don't see that one on here. I'm looking at the like other mock quiz.
okay, maybe I put the solutions to the actual quiz, which means I need to make a new quiz now. Yeah. So this is the. Is this what you're seeing? Actually, that's. I made my point. So this is the solution process. If we can see it after class. Okay. Yeah. So this was the quiz I had planned. Now I need to change this, of course. So this is one more example problem for you to do. Okay. So here's the function log of 1 plus x minus sine x. That's what you need to solve for. And you would be able to find 3 roots, 2.55, 7.47, and then 8.13. Okay. So this is also, I'll post this. Here is one more practice quiz for you to take. Okay. Like a second mark. So if you had chosen the other guess, that is, instead of guessing 1, if you had guessed something closer to the other root like a 0 or a 0.5, you will get a completely different solution. What is that solution? Here is guess 0.5, function, derivative, next value. Repeat, function, derivative, next value. If you go through this, 0.4397 is the other root. Just like 1.1436 is one of the roots. So there are two roots. And do you understand why there are two roots? Look at the graph. There are two points at which the intersection takes. One obviously is between or less than 0.5, so 0.43 makes perfect sense. 1.14 also makes perfect sense. Okay. I'll give you a minute to complete what you're writing while I talk to him for 1 second, and then we'll continue. Yeah. Yeah. And your point?
It doesn't have.
You need to download it. You need to download and open it in MS Excel for you to see all the sheets. Okay, have everybody finished writing? You're all good with Newton-Raphson? What I would suggest is you doing more examples like what I've put in the homework set. Use my Excel sheet or build your own Excel sheet with mine as a guide. Use the Excel sheet to cross-check your work. And once you have understood how the method works, how you can do it, several iterations, after that, you can just use your Excel sheet to run through problems and quickly do more. Okay. In the exam, where we'll have like 60 minutes and maybe 3 or 4 problems, I will allow you to bring your computer. You can use your Excel or MATLAB. I'll say, here's a problem. Use your Excel or MATLAB to solve and fill in the blanks. I'll try to show my smarts in how I craft the question, and you show me your smarts in how you can use Excel or MATLAB. I'm not looking for like genius here. What I'm looking for is competence. Whether you could work a program to implement an algorithm or use the program to solve a problem. Okay. Any questions before we move on to the next topic? Yes, no questions? All right. So, Newton-Raphson is, you got the idea. That is, you guess a value for the root, you compute the local slope, and from the local slope, you set this equation up, and you are able to get a value. Except there is one problem here, which is this function I gave here is easy to differentiate. Not every function is that convenient for differentiation. It's easy to evaluate a function. If you know the function's formula, you can evaluate it. And then you can compute f of x. But differentiation is not always easy because of two reasons. One is it is not easy to automate differentiation. Unless you know the function and its derivative analytically, it's not easy to automate. Number two, not all functions come like this. Can you think of another way to represent a function that is not like an equation? How else can we represent functions? Piecewise functions is one. They are not easy to differentiate, but they are like still mathematically, you can write them in different intervals. That's one way. Good. Can you think of one other way? As engineers, what do? you collect data. It could be an experiment, it could be a survey, it could be a numerical simulation. You collect data. How is data usually organized? Table has XY pairs. The independent variable X, comma, a dependent variable Y or f of X. A abscissor and an ordinate. A dependent and an independent and a dependent. So you could be getting data that is representing some function which you don't even know, but that data could come as a table. And in fact, most data originate as tables and not as functions. You would be surprised to know that if you are having a torque transducer measuring the torque on a shaft, God knows what the torque is going to follow as a function. What you really get is a sensor, the output from the sensor as a long table of data, and you need to figure out what that function is. It could be a sinusoid, could be an exponent, it could be anything. But usually, you would agree with me when I say you don't know what functions are going to be describing your data. Would you agree with that? You are all biomedical engineers, right? If you are going to represent the ECG of a subject, you don't know what the function is. If it is sinus heart rhythm, even then it looks like somewhat like a chaotic thing. It's not easy to represent everything using functions. So when you have data, when you still want to get the roots of functions which are represented here as data rather than as equations. Like for example, if I say this, if this is a known function, that's easy to understand, right? There is a curve that describes the function. Suppose the function weren't given to you as an equation, but rather as data that looks like this. That this is your data. It doesn't even have a value when it exactly intersects at 0. All you have is you can draw a line like a curve fit that runs through the data, and then you are asked to say, when will this function attain 0? Well, 0 is not even on my tabulation. How am I supposed to say when will it attain 0? That is really the need for a method which doesn't rely on computing this derivative analytically. We need another way of doing this thing. How else can you do this if you need slope but can't have the function or can't have the derivative? Answer this question, the answer will come to you. If I want the slope of this function at this point, what should I do? Slope. Sorry?
Rise over run.
The louder please.
Rise over run, like on that.
You want to draw this and say this is, let's say, delta y and this is delta x. I'm going to say slope. I'll approximate it as delta y over delta x. Right? That's what you're saying.
Yes.
Where else in real life do you do this either mentally or you do this consciously to get the slope or the rate of change of something without even thinking about it? You all do this. Except you're not, when you do this, you aren't thinking about math or engineering. Now I want you to make the connection. Can I help you get started? I want examples. I won't let you go until you think for yourself. If you are driving down an incline, like a steep hill, if you look at the rate at which your view is falling, you kind of your brain approximates the grade. If you know it's a 10% grade or a 5% grade or a 1% grade, you likewise adjust your braking and your speed of the car so that you don't roll over. If it's a 10% grade, your brain automatically knows. If you know driving, it automatically tells you slow down. You need to apply the brakes and go slowly. It basically looked at how much the elevation drop was and how much distance you travel, and it gave you the grade in your head, even though the board might say 10% or 8% or whatever. Even before that, your brain knew that. That is one example. Yes.
Golf, putting,
Okay, I'm not a golfer. You need to explain.
like when you roll a ball up a hill. And then you want it to end at a certain distance, you have to measure the height of the hill, right?
So you estimate it visually
Yeah, so how high you throw it, so it rides.
so that it
False.
compensates for the increase in
Yeah.
elevation.
Yeah.
Okay, good, similar, like I'm talking downhill, you're talking uphill. Good, other examples. So golf and driving are taken, so you have to think more. Think spatial derivatives, think time derivatives, speeds, rates. It's not an example that I wish any of us to be in. If you are in an elevator and for a few seconds, if the elevator was a free fall, how would you know? You would feel your lunch rise up, this person. Your lunch is at in your belly, it's at rest, but suddenly if you start free falling, that food isn't falling, you are falling down, but the food is in place, so it will basically travel up. If you feel that your belly is you're feeling a little bit like emptied, that's because the elevator is in damn free fall and you need to hit the fire button. Okay? Where else do you feel speeds, accelerations? Yes.
Plane taking off.
Plane taking off. That will be like somebody is pushing you back. That's inertia working against you. Okay? This is basically speed or acceleration. Other examples, one more. Not related to free fall or ascent, which we have covered now. One more example. Where else do you get slopes?
Like down a mountain and you like start going down.
Same thing as I said. It's a little bit slower than what I said. You know, your eye inspects the elevation change and the distance, and it correlates them. Yeah.
See like a waterfall, like the water's moving out of.
So falls, descent, ascent, they are all from the same family. Let's leave them alone. Think one more example and move on. Okay, good. Biomedical engineers are thinking. What about the heart rate? Okay, what about the heart rate? Tell me, explain.
Like when you have bradycardia, like you're at rest, so then there's a slower rate.
All that you can perceive if you have the EKG next to you. But if you are the person, you are the subject, how will that feel to you for you to think, oh, this is tachycardic, I need to call Dr. House? How will you perceive it? This is my question. It's not about looking at the data and then figuring it out. That's what doctors are for. How will you perceive it and spot something? That's the question. Those are symptoms. I'm asking about perceptions. Your senses, how will they tell you something is happening?
You're not feeling.
Are you still talking like a biomedical engineer? Think like a mechanical engineer, please. Yes. Being lightheaded is a symptom for many things, not just diabetes. Yes.
You can count time with.
See, you count, what do? They look at the clock while holding your pulse. So if your pulse rate is erratic, every 15 seconds, you get a different average. That means you are tachycardic. That's what I was looking for. How do you perceive it? Okay, good, nice example. Okay. All right, good. So we are all thinking about the rate at which something changes divided by an independent variable, which could be space or time. And we are going to say that if you have a tabulation of data, the slope is as good as getting the derivative, the analytical derivative. So a second variant of the Newton-Raphson method called the secant method, which operates like this. Okay. So we say here, I'm going to erase this. All right. So you have f dash of x I equal to f of x I minus 0 divided by xi minus xi plus 1. This is Newton-Raphson. This is Newton-Raphson. Okay, from this we rearrange and get xi plus 1. Secant method is a little bit simpler, where we say f dash of xi is f of xi minus f of xi plus 1 divided by xi minus xi plus 1. We don't replace it to be 0. Here we consider f of xi plus 1 equal to 0. Here we don't. Okay. And we rearrange this to write xi plus 1 equal to xi minus f dash of xi is equal to f of xi minus f of xi plus 1 divided by f dash of xi. I'm just rearranging it. Okay. Then I'm going to write f dash of xi is xi minus xi minus 1 is f of xi minus f of xi minus 1 divided by xi minus xi minus 1. That is, it's if I say this is I and this is I plus 1, this is I minus 1. So I'll say this is previous, this is current, this is new or next. Not in a spatial or a time sense, but in an iterative sense. When you do your iterations, this is the previous iteration, current iteration, next iteration. Okay. So if I put this back in here, if I put this for f dash of xi, put this for f dash of xi, I'm going to get xi plus 1 equal to xi minus f of xi minus f of xi plus 1, okay, minus f of xi plus 1 divided by f of xi minus f of xi minus 1 multiplied by xi minus xi minus 1. Just substitute it back here and this is what I get. If xi plus 1 were to be the root of f of x equal to 0, then f of xi plus 1, next line, then f of xi plus 1 may be taken to be 0. Because that's what a root means. So I can set this to 0 again, which finally gives me xi plus 1 equal to xi minus f of xi divided by f of xi minus f of xi minus 1 times xi minus xi minus 1. This equation or this scheme is called the secant method. Okay, so here is one observation or observational question for you. This is the equation for secant method. This is the equation for Newton-Raphson method. To get started here, you need a guess. You need I equal to 0, which is your initial guess. So you would say xi equal to something, let's say 0.0 or 1.0 or whatever. You need one guess to get started because this involves I and I plus 1. Current and next. Secant method, on the other hand, in order to get next, you need both current and previous. You need two guesses. Okay, so Newton-Raphson needs one guess to get started. Whereas secant method needs two guesses. They don't have to form a range or anything, but you still need two guesses to get started. What is the main advantage of secant method that I mentioned? You don't need to have a function that's either differentiable, or you don't need to have an actual function. If you have only tabulations of data, that would still work for secant method, but not for the other. So any data that comes straight from the laboratory that you just have it as a tabulation, only secant method can help you, not the other. So you might almost expect this. If it's an analytic function, it can be Newton-Raphson method or even the secant method. But if it's a tabular data given to you as like a long set of values, it can be only secant. Okay. Are we ready to do the same example now with secant method? You want to try? Okay. So let's recall the function. The function is f of x equal to e power minus 0.1 x minus sine 2x plus cos 4x. That's the function. I want you to now solve for f of x equal to 0 with an initial guess of, let's say, 1. You still need two guesses. We'll say this is like 0.9 and this is 1. That is, for secant method, you need both the previous and the current in order to get started. When all of you are done with this side, please tell me, I'll need to erase it. Everyone's done with the right side? Yes, yes. Good. What is your name? Good. Yes. Good. And the other thing is that for the quizzes, the one on Thursday, for example, it will be a very simple, straightforward, solve this kind of statement. For the exam, you can also expect word problems, like something that needs you to read it and then figure out what the equation is and then solve it. Okay. All right. How do you do this? What have we learned so far in this class about solving iteratively? Who's having those 3 words I'm looking for? Maybe 4 words. Make a damn table. That's the 4 words. All iterative techniques make a table. Okay. Iteration number. And then we'll say xi minus 1, xi, f of xi minus 1, f of xi, and then you have xi plus 1 equal to xi minus f of xi divided by f of xi minus f of xi minus 1 multiplied by xi minus xi minus 1. Wow, I didn't know I could memorize things. My wife would be impressed. And then there has to be a residue. I think I am running out of space, so I'll write it here. Residue. My function is e power minus 0.1x minus sine 2x plus cos 4x equal to 0. My initial guess, so this is, you can call it I equal to 1, which means this is x0, this is 0.9, and this is x1, this is 1. Now you start. Evaluate the function at 0.9 and then at 1, and then compute this value. What is f of 0.9? Are you getting these right? For the 0.9 and 1, the value of the functions. So now xi plus 1 or x2 equal to x1 is 1, f of x1 is minus 0.6581 divided by minus 0.6581 minus minus of 0.9567 times what is xi? 1 minus 0.9, which is equal to, you tell me, Value
0.22.
1.2204 is, are others getting this? Yes. Too easy? We'll spice it. Okay, so when you go to the second iteration, your previous becomes whatever is the current. So x1 is 1, and then x2 is whatever you computed here, 1.2204. Compute the values of the function, and then you compute x3 equal to 1.2204 minus, and you can fill in the blanks. So do that, tell me the answer. We have 11 minutes. So if you are done with this iteration, what I'm asking you is to continue and complete this on your own time. And I want to say a few more things. What are we getting? Anyone? Yeah. We have a value
0.85.
0.8535. Okay, is anyone else getting this? I don't know if you're going towards either of the roots because we know the value of the roots. One is 1.1436, the other is like 0.4353 or something. So this is not heading towards either of them. Maybe you need to check. But anyway, if you can look up, take a pause, please look up, complete this. Okay. You'll on Thursday, we'll have two problems, that is clear. Those two problems could ask either bisection or Newton-Raphson or secant method. Three methods, but only two problems, only, which means only two are going to appear on the test. Okay. So practice enough examples. Okay. Do the mock. I'll also post what I thought was the real quiz, which is now also a mock. Okay. I'll make another quiz. Now, I want to make a couple of points here. All right. So if you go to the syllabus posted on your Canvas, you go to the syllabus posted on Canvas, I have these links, which are the course materials from last fall. If you click the fall 23 course material, it opens up another OneDrive folder. Okay, and you can see all my previous exams, previous Excel files, and so on. So if you click module 1 examples, which is what this file is, you can see many more examples done on each technique: bisection method, false point method, Newton-Raphson method, secant method. So here's a Excel sheet or a formula sheet for secant method, which is ready to go. You can take it and use it. Everything is for you. Okay. So I would suggest that you take this problem that we just tried. You use this sheet. You'll need to modify it, of course. But if you know how to modify it, basically you understand the technique. So there are many more examples for you to try. Okay. So there is Newton-Raphson, there is bisection, there is secant method. I always hated false point, so that's why I didn't care too much for it. But these three methods, if you practice, you should be in good shape. On Thursday, we'll still do problems related to these in like 45 minutes. So maybe we'll give one problem to each and introduce it and wrap up this chapter. Okay. Questions about the test, about preparing for the test? How many examples have you tried so far? Touch your heart and tell me the truth. Two examples. Others, 4, 1. Broadly speaking, not enough. You need to practice at least like 4 or 5 problems per method, or take the same problem, solve it using 3 methods. If you could knock out 5 to 10 examples, and if you time yourself and it takes 20 minutes or less, that is means you are practicing to be competitive on the test. Mostly the test will be easy, but it will test you in the sense that you are able to do it quickly and accurately so that you can get to all the problems. Okay? If you take 40 minutes for one problem, that's not going to be very good for you. Okay. All right. Shall we still have 5 minutes. I thought this will take longer to say. Shall we do this problem using this Excel sheet? I'll modify it in front of you so that you can actually see it. Okay. All right. So if you take secant method, okay, what is the problem here? The problem that I had solved is f of x equal to x minus exponent of minus x. Whether it is said explicitly or not, what do you always do? Say it loudly. Use the graphical method to get an idea of what the answer is, or how many roots are there, where are those. Okay. So in this case, we had like 0 and -1. I'm going to modify this for our problem so that you can see it. Okay. In 4 minutes, we'll see if that works out. Okay, I'll just do it here, doesn't matter. So I have f of x is exponent of minus 0.1x minus sine 2x plus cos 4x. That's my function. Okay, and I have iteration 1. I'll erase all this to okay, I'll erase all this. Okay, so I have iteration 1. I have x I minus 1, and then I have xi. Okay, I'm going to say my guess value is 0.9 and the other guess value is 1. I have f of x I minus 1, which is, how do you, this is where you need to change the function. You need to enter this function and evaluate that this and this value. Okay, is that clear? Not too fast. I still have only 3 minutes. Minus 0.1 times x minus sine 2 times x plus cos 4 times x. Okay. And then to evaluate this, I'm just going to copy and paste it to the right. Automatically, since this is only one cell to the right, it will copy over. And here comes the main formula. This is xi minus f of xi divided by f of xi minus f of xi minus 1 times xi minus xi minus 1. Nothing to it. Okay. 1.2204. Good. So far, so good. How do you compute the residue? What is residue? Correct. Absolute value of new divided or new minus new divided by the old minus 1. Okay. So this is around 22%. Right now, it's starting at 22%. Okay. For the second iteration, what is the value of xi minus 1? It's 1, but how do you write it symbolically? How do you say it as a algorithm in a algorithmic fashion? Whatever is the new xi minus 1 is the old xi, right? So you just need to write this is equal to whatever is on this cell. That is programming. If you just keep saying the actual answer, that is called hard coding it, meaning you are just saying the answer. It's literally will work only for one problem, not for every problem. Okay. So we have this. And what should be xi? Whatever is H cell in cell H3, right? So it should be whatever is in H3. And computing the function is easy, just copy paste it. Computing the new value is easy, just copy paste it. Computing the relative error is easy, just copy paste it. So now you are down to 6.9% error from 22%. Okay. So then we'll do iteration 3. Now actually it got even simpler. All you need to do is copy the previous row and paste it. You are getting a residue of 0.65%. It's gotten down much smaller. Okay. And iteration 4, iteration 5. So for a root of 1.1436, we satisfy the condition that the residue is below 10 power minus 6. Okay, so the value we were getting this is wrong actually. It's going 1.1436. This is what we also got when we did Newton-Raphson, if you remember. So this sheet right here is now modified for your problem. If you can understand how to change it for any problem, you understand the method. Okay. So I'll see you on Thursday. Be on time. If you're late, you lose that time. I'm very clear. I won't give extra time. If you're late by 10 minutes, your test, you lost 10 minutes.